So we just showed that this simple function is a linear transformation by checking these two conditions. What if I give you this function, sine function? Is this a linear transformation? Not necessarily. Why is that? You can find a counter example. You can show that sine of x plus x1 plus x2 or sine of x plus y is not necessarily equals to the sine of x1 plus sine of x2. The counter example can be pi over 2 and pi over 3. Sine of pi over 2 plus pi over 3 is not necessarily the summation of sine of pi over 2 plus pi over 3. So here we introduced a counter example. So if I give you a function and I ask you that function is a linear transformation or not, if you have a counter example, you can easily use that counter example. So sine function, cosine function, those are not example of linear transformation. Those are non-linear transformation. We are not going to discuss non-linear transformation in this class. Our focus in this class is on linear transformations. We have a nice theorem. This theorem lists nice properties of linear transformations for us. Suppose T is a linear transformation from vector space V into vector space W. Suppose we take two vectors from the domain. Then you have the following properties. First of all, linear transformation takes zero vector in V and it gives you zero vector in W. So zero vector in V might be different from zero vector in W. You need to be able to differentiate between them. If you multiply a vector by -1 or the opposite of the vector, the linear transformation say, okay, no worries. This is just a scalar C. Based off of the definition and preservation of scalar multiplication, this becomes -1 times T of V. So the negative sign can be written in front of the linear transformation. As it preserved the addition, it also preserved the subtraction. The subtraction or difference between two vectors under linear transformation is the same as their difference of the linear transformations. But again, please note that this operation is in V, and this difference belongs to W. Again, if you have different vector spaces, these operations are going to be different from each other. And finally, one of the most important observations is if you have a linear combination of vectors, and if you just plug that into a linear transformation, it becomes the linear combination of these terms. So T of C1 V1 becomes C1 T of V1. T of C2 V2 becomes C2 T of V2. And finally, T of Cn Vn is Cn T of Vn. So again, it preserves the linear combination, which is very important. If you plug in a linear combination of vectors into a linear transformation, it gives you a linear transformation of these linear combinations. For example, consider this linear transformation. T maps the space to the space. Suppose it has the following properties. If you plug in 1, 0, 0, or as you remember, the standard bases into this linear transformation, it gives you 2, -1, and 4. This linear transformation also takes 0, 1, and 0, which is, again, a member of standard bases. It gives you 1, 5, and -2. This linear transformation takes 0, 0, and 1, again, another member of the standard bases. It gives you 0, 3, and 1. Now the question says, well, what if now I plug in 2, 3, and -2? What happens here? What is the output value? Well, okay, let us begin. I have 2, 3, and -2. Is there any way that I can take this vector and write it as linear combinations of these vectors as members of standard bases? It's not that difficult to see that. It can be written as 2 times 1, 0, 0 plus 3 times 0, 1, and 0 minus 2 times 0, 0, and 1. This is the linear combination that you have. But we just learned that if we have a linear combination of vectors, the linear transformation basically preserves them. What's the meaning of that? It means that if I plug in this vector as an input value into this function, it becomes 2 times t of 1, 0, 0 plus 3 times t of 0, 1, 0 minus 2 times t of 0, 0, 1. I just need to write each scalar outside of t of v1, c2 times t of v2, and so on. Well, I know t of 1, 0, 0 is 2, -1, and 4. So it becomes 2 times this component, which has output 2, -1, and 4, plus 3 times 1, 5, -2, minus 2 times 0, 3, and 1. Well, the rest is easy for you. You just distribute 2 into parentheses. You distribute 3 into parentheses. And basically add the vectors -2 into parentheses. And then add the first components, add the second components, add the third components, which becomes 7, 7, and 0. So this linear transformation takes this vector, which is a linear combination of these vectors, and it gives you this output value. So the image of 2, 3, and -2 is 7, 7, and 0, or 2, 3, -2 is the inverse image or pre-image of 7, 7, and 0. Next example for you. Suppose we define a function that maps plane into space. This function takes vectors from the plane and then multiply them by a matrix like A. And it is the matrix multiplication. You have matrix A, 3, 0, 2, 1, -1, and -2, and vector V is V1 and V2. Now question says, find T of V and then show that T is a linear transformation. Let us begin. Since V is equal to 2 and -1, it means that wherever you see V1, you're going to use 2. Wherever you see V2, you're going to use -1. T TV as is defined as AV becomes 3, 0, 2, 1, negative 1, negative 2 times 2 and negative 1, matrix multiplication. So basically we're going to take the first row, multiplied by first column, and then continue the process. This becomes 3 times 2 plus 0, which is 6, then 2 times 2 minus 1, which is 3, and then you have negative 2 plus 2, which is 0. So as you can see, this is a vector in the plane, and this is the result, which is a vector in the space. Now, to show that T is a linear transformation, take two vectors u1, u2, and v1, v2 in the plane. If you add these two vectors together, u1 plus v1, u2 plus v2, then tu plus tv, as is defined, is au plus av, which is equal to a times u plus v. If you calculate a of u plus v, it is basically the multiplication of this matrix by the vector u plus v. So the same process as we saw before. We're going to take the first row multiplied by this column and continue the process. So it is 3 times u1 plus v1 plus 0 times u2 plus v2. Then 2 times u1 plus v1 plus 1 times u2 plus v2. Then negative 1 times u1 plus v1 plus negative 2 times u2 plus v2. This can be written as 3u1 plus 3v1. Then you have 2u1, 1u1, and so on. So now this is your left-hand side. What about the right-hand side? What is tu plus tv? If I just add these together, what happens? I have au plus av. So if I add these separately, a times u plus a times v, does it result the exact same matrix? Well, let us begin. So I'm going to multiply a by u, then I'm going to multiply a by v, and then add the results together. So again, the same process as we saw before. The first row times the first column, which gives you 3u1 plus 0u2. The second row by the first column, it only has one column. So you get 2u1 plus 1u2, and so on. The same process for the matrix multiplied by vector v. 3v1 plus 0v2, and 2v1 plus 1v2, and so on. But if I just add these two matrices together, this is basically 3u1 plus 3v1. So far, the very first entries are the same. You can check the rest of them. These two are the same as well, and these two are the same. So basically, you're saying that, hey, these two matrices are the same. But what's the meaning of that? It means that you just showed that this function preserves the addition. Tu plus v is the same as tu plus tv. So the first condition is basically met. Now we just need to check to see if scalar multiplication is met as well or not. So let us move on to the next slide. Okay, suppose k is a scalar. T times kv can be written as a times kv. But k times v is kv1 and kv2. Then you're going to multiply matrix A by this vector. 3, 0, the first row multiplied by the first column, and so on. This is 3 times kv1 plus 0 kv2. 2 times kv1 plus 1 times kv2, and so on. But This is nothing but 3kV1 and then 2kV1 plus kV2 and so on. You can easily factor out k, right? Here you have your k, you have a k in linear combination down here. So by scalar multiplication, you can basically take your k and write this outside the matrix. Due to matrix multiplication definition, this is k times TV. So this is how we defined TV. 3 times V1 plus 0 V2, 2 times V1 plus 1 V2 negative 1 V1 minus 2 V2. So as you can see, the scalar multiplication is also met. So we just showed that this function is indeed a linear transformation.